During this report period, the Flight Crew Support Division has increased its support of upcoming Gemini and Apollo operations. The advent of manned Gemini missions accents the role of FCSD in the training of flight crews and in the implementation of crew-oriented mission tasks. The Flight Crew Support Division has acquired several important pieces of experimental and training equipment, including Gemini Mission Simulator number 2, now installed at the Manned Spacecraft Center in Houston, Texas. At present, it is being used to train the GT-4 flight crew. Every portion of this flight can be simulated from liftoff to touchdown. While Gemini Mission Simulator number 2 is in the GT-4 configuration, Gemini Mission Simulator number 1, located at the Kennedy Space Flight Center, is configured for GT-3. An alternating relationship of this sort will be maintained to assure consistency of training for future missions. Visual displays will be added to the Gemini mission simulators, giving rendezvous capability to support training for advanced Gemini missions. The last 100 feet of rendezvous and the docking maneuvers will be practiced by the astronauts in the Manned Spacecraft Center Gemini Translation and Docking Simulator. This is a moving base simulator with 6 degrees of freedom. It consists of full-scale mock-ups of the Gemini spacecraft crew station and the docking end of the Agena target. The cockpit of the crew station duplicates that of a Gemini spacecraft. Control devices necessary for docking are operational, including the translation control and attitude control. Displays and readouts needed during docking are also operational. This includes the range rate indicator, attitude indicator, and propellant pressure and quantity gauges. The crew station supplies 4 of the 6 degrees of freedom. These are lateral translation and the 3 rotations, pitch, roll, and yaw. The Agena target provides the remaining 2 degrees, longitudinal and vertical translation. Simulations are monitored from the adjacent control room. The equations of motion governing the simulations are programmed on an analog computer. Closed-circuit television provides an overall exterior view of the simulation. The instructor's console has instruments duplicating those in the crew station. The instructor is also able to introduce system failures for which the astronaut must compensate. All trainer motions prior to docking are derived from the astronaut's control of the orbital attitude and maneuvering system. Both the Gemini and Agena are supported by air bearings running on steel rails. A status display panel is located on the Agena above the docking ring. This provides the pilot with Agena systems information needed in orbital missions for docking and subsequent powered maneuvers. After completing the docking, the pilot unlatches and maneuvers out of the docking position. The Manned Spacecraft Center Gemini Translation and Docking Simulator is an essential part of the astronaut training program and an important engineering evaluation mechanism. Another docking simulator is the cable-suspended moving base docking simulator at NASA's Langley Research Center. Upon completion of Gemini Agena docking studies, this engineering simulator was converted to an Apollo Lunar Excursion Module configuration. The target is a statically mounted full-scale mock-up of the Apollo Command Module. The pilot flies the simulation from a horizontally mounted LEM crew station. He lies on his back in a support couch. This is required by the horizontal facility, but will not be a part of the actual LEM. These simulations are further studies of the overhead window docking techniques begun at the Manned Spacecraft Center by FCSD. Several areas are under study: rate command and direct control modes, vision and visual aids including sunlight, ambient light, and paint schemes. A continuing program of engineering and training simulations is a part of the overall division support of coming missions. Mission support is also given in the area of flight planning. The Spacecraft Operations Branch of FCSD compiles the flight plan for each manned spaceflight mission. The GT-3 flight plan, now being prepared, contains all planned details and procedures of the first manned Gemini flight. It will be carried in the spacecraft during simulations and actual missions on a special flight plan readout, photographed on rolls of 90mm film. The flight crews crank the film through the reader manually. The Spacecraft Operations Branch maintains liaison with and receives inputs from all offices concerned with the Gemini mission. Up to the time of the mission, the flight plan undergoes constant review. Revisions are made whenever necessary. Flight controllers in the Mission Control Center and in tracking stations around the world will have copies of the flight plan. Portions of it can be shown on the projection screens of the Mission Control Center. Here, too, the flight plan is used for simulations as well as actual missions. The flight plan for GT-3 is the blueprint for the first manned Gemini mission. The Flight Crew Support Division is also active in its support of advanced Gemini and Apollo missions. In this study, the test subject uses muscle power to change body attitude during simulated weightlessness on the Balanced Extravehicular Training Aircraft, or Beta Trainer. The Beta Trainer is composed of three basic parts. The top platform is a dished spherical section with a radius of curvature of 40 inches. This approximates the vertical distance from the bottom of the feet to the operator's center of gravity when standing. The second part is a cylindrical plenum chamber which creates two air-bearing surfaces, one between itself and the dished platform, the other between the plenum chamber and the floor. The third section is a toroidal pressure tank for storing the air on which the Beta Trainer rides. The trainer rides above a 21 by 24-foot floor composed of machined and ground machinists' layout tables. The Beta Trainer rides about 1/1000th of an inch above this floor. The accuracy of installation of this floor was extremely critical. The overall alignment of the level was held to approximately 3/1000ths of an inch. The joints line up to within 3/10,000ths of an inch. Because airborne dirt and dust collect on the finely machined floor, a clean room was built to protect it. The first item to be tested on the Beta Trainer is a handheld extravehicular propulsion unit. A single thrust nozzle points forward and twin nozzles point to the rear. This device is designed to be used by an astronaut outside an orbiting spacecraft to propel himself in space. Thrust is supplied by cold gas stored under pressure in tanks attached to the trainer operator. When the trigger mechanism is pushed forward, the pressurized gas is released through the front nozzle and the propulsion unit operates in a pusher mode. When the trigger mechanism is pulled back, the two rear nozzles are actuated and the propulsion unit acts in a tractor mode. The Beta Trainer is entirely self-contained, simple, and economical. The operator can use it while in shirt sleeves or in a pressure suit and can move freely, unrestrained by harnesses. The direction of gravity remains constant. The Beta Trainer's low weight and construction provide accurate duplication of the inertial forces acting on the operator. In the study of advanced Gemini mission problems, the Beta Trainer is a valuable tool and marks a step forward in the development of simple air-bearing systems. In support of Apollo lunar landing missions, the Flight Crew Support Division, in conjunction with the Flight Research Center, Edwards Air Force Base, California, is developing the Lunar Landing Research Vehicle. The Lunar Landing Research Vehicle, designated the LLRV, is a prototype of a free flight simulation vehicle to train flight crews for the descent to the lunar surface. The main thrust engine of the LLRV is a gimbaled CF700-2V turbofan jet engine. This engine supplies full thrust for the ascent phase of the LLRV flights. During simulated lunar descent, the engine is automatically controlled to support 5/6 of the vehicle's weight. A total of 8 hydrogen peroxide lift rockets, each developing 500 pounds of thrust, are attached to the vehicle. 2 are primary and during lunar simulation support the vehicle in conjunction with a turbofan engine. The other 6 engines are for emergency backup. Attitude control is provided by hydrogen peroxide control rockets, adjustable from 18 to 90 pounds of thrust. The electronic guidance package, which controls the gimbal mechanism of the turbofan engine, is mounted on the rear platform of the LLRV. The pilot station is forward of the turbofan engine. the pilot sits in an ejection seat similar to those in the Gemini spacecraft. Present controls are similar to conventional aircraft. As the pilots become more familiar with the LLRV, the controls will be updated to a system similar to those of the Lunar Excursion Module. A manual throttle is used to control the turbofan engine during the ascent stage. An auto throttle switch located on top of this throttle will be used by the pilot to actuate automatic controls for the lunar descent simulation. The pilot uses another manual throttle to control the lift rockets. A shock absorber with 14 inches of travel is located at the base of each landing leg. The entire framework of the LLRV is lightweight aluminum tubing. Using the turbofan engine, the LLRV takes off and descends vertically to 1,700 feet altitude. The pilot initiates a horizontal velocity and puts the LLRV on auto throttle. This begins the descent stage with the turbofan engine supporting 5/6 of the vehicle's weight. At 1,000 feet, the pilot initiates the hydrogen peroxide lift rockets and begins the simulated lunar trajectory. At 500 feet, the descent is stopped and the pilot flies the LLRV horizontally while selecting his landing site. The pilot then descends vertically to his selected landing site. The duration of the lunar landing simulation from takeoff to touchdown will be approximately 2.5 minutes. The first flight tests of the Lunar Landing Research Vehicle were held on October 30th, 1964. During these first tests, only the turbofan was used for lift. 3 takeoffs and landings were flown. Later flights initiated the lift rockets and the LLRV was maneuvered at higher altitudes. These early flight tests were highly successful. The first full lunar simulation flight is scheduled for early 1965. The Flight Crew Support Division has put into operation a number of training and evaluation devices. The GT4 flight crew is training on Gemini Mission Simulator number 2. The Gemini Translation and Docking Simulator is operational, and the astronauts are beginning their training on it. On the Langley Research Center Moving Base Docking Simulator, studies of overhead window LEM Apollo docking techniques and crew evaluation tasks are being conducted. The preliminary GT3 flight plan has been compiled. The process of revision will continue until shortly before the first manned Gemini flight. In support of advanced missions, FCSD has started studies of extravehicular mission tasks using the simplified air-bearing Beta Trainer. The Lunar Landing Research Vehicle is now undergoing flight tests. This is the forerunner of the free flight simulator designed to train flight crews to make a successful lunar landing in the Lunar Excursion Module. The acquisition of this hardware has enabled the Flight Crew Support Division to strengthen its support of manned Gemini and Apollo missions.